uh, I will be talking about a number of different subjects that have caused a lot of excitement in the scientific community worldwide. And many of you are very familiar with these words, and some of you may not quite know what these really are. And that's what I will try to clarify to you. Hopefully that will help some of you. The topics will be Big Bang, dark matter, dark energy, black hole, neutrino, God particle, Higgs field, gravity, expansion of universe, and search for life elsewhere in the cosmos. And so I will try to cover all of these topics within the time that we have. So I may have to go a little bit faster, and please excuse me for that. First of all, I will be talking about the Big Bang. What is Big Bang that we hear so much about? We will be talking about a lot of different sciences. And in scientific approach, I want to point out that in scientific approach, there has to be some type of an evidence, or it is visible directly or indirectly, or some of its effects has to be there in order to be accepted. And so with that, we are starting that what is Big Bang? According to the Big Bang theory, the universe began by expanding from an infinitesimal volume with extremely high density and temperature. It started instantaneously from an extremely small volume and extremely high temperature and pressure. That is Big Bang theory. Now, why do we think that this Big Bang happened? Some of us are familiar with the Quranic word that lahu kun fayakun. Allah subhanahu wa ta'ala says be, and it happened. We are very familiar with that Quranic verse. But from scientific point of view, what are the scientific community saying? Why we think it happened? The number one item is that the universe is expanding. The world, the universe where we live, it is expanding. It is getting larger. And at an accelerated rate, not at a uniform velocity, but an accelerated rate. As it expands, it expands faster and faster and faster. Then, Big Bang perfectly explains the abundance of hydrogen, deuterium, and helium in the universe. If we look at the entire universe, not in this world only, well over 90% of the all material that we have are hydrogen and helium gas. How did that happen? Where is our gold and platinum and iron and nickel and carbon and oxygen? Where are those? Big Bang explains that. Big Bang explains why it is expanding. And he also says that observation of cosmic background radiation, the afterglow of the explosion from every direction in the universe, that when this explosion took place, Big Bang happened, it was 10 to the power 37 degree Kelvin temperature, extremely high. But after that, it has been slowing down, it is cooling down, and the temperature now is about only 2.73 Kelvin. And that is also explained by Big Bang theory. So these are some of the scientific reasons why scientists feel that the Big Bang happened. Yeah? Okay, so what happened? This is after 1 second. 1 minute, 1 hour, 1 day, 1 year, 100 years, and then it goes up to 14 billion years up to this point. That is where we are now. And so what happened after 1 second? I will go into that what happened before 1 second, but within 1 second, as soon as it was, once again, the temperature was 10 to the power 10, which is 9 billion degree Kelvin. And at that high temperature, there was no material. There was no electron, proton, or neutron, or hydrogen, or helium. None of the materials were there. It was all complete energy. Energy. Because at that high temperature, no material. Like, if you heat a piece of iron, 2000 degrees centigrade, it will melt. It cannot be even solid. So how can you have a billion temperature? How can material exist? Not only even the quark did not exist, not to speak of proton or neutron. So at that high temperature. And so, and then as it started to cool down to here 10 billion temperature to going down, and up to here at about this stage where there were 100,000 degree, after 100,000 years, that is when, as it cooled down to about 10,000 degree Kelvin, that is when the energy were transforming into matter. Because I will be mentioning that energy and matter, before we used to think that energy is conserved or matter is conserved, but after the special theory of relativity, E equals mc square, some of you may be familiar with it, total content is energy plus matter, because they can exchange, they can transform one into other. So the total mass energy was taking a transformation at this stage of time and temperature, where the energy density and the matter density became comparable. And after that, the matter became dominant. So that is what the phase. So we have not talked about what happened before 1 second. After 1 second, it was cooling down. It was all energy. And at this time and temperature, it was cooled enough so that the energy was transformed into matter. And ultimately, matter was dominating. And okay, now, if the universe is, if Big Bang happened and all the stars are all over the place, and if we look at the sky, why it does not look bright continuously? Because if there are stars all over, if we are in a park, at a national park, and if we look around, the trees are all over the place and we cannot see beyond. So the stars are in the sky like that. So how come we are not see the sky totally bright with sunlight? That is because the light takes time to travel. At a park, the trees are nearby, so the light can come from there. But these are billions and billions of miles away. These are like light years away, so it takes time for light to come. So that is why some of the lights have not even come from some of the stars and galaxies yet. So the universe that we see is where from the light had the time to come to our place. So the visible universe is finite. The visible universe is finite. That is the sentence here. And that is why we cannot, we don't see, we see the sky is dark, because in the part that is not a star there, the other part, those light from the star where those dark areas are, has not arrived at our place yet. And if it does not come, for example, when the sun sets, when the sun sets, we still see that sun for another 8 more minutes. Why? Because 8 minutes ago, the light that started from the sun has just arrived. By that time, in 8 minutes, sun has gone down. So we don't see, we see what happened 8 minutes ago. And we see what happened 10 billion years ago, because that light takes time to travel. Okay? So how is it that this universe is expanding? We see that the galaxies are moving away from us. So this is one of the ways to see that if an object or if a chair is moving away from me, then I know that it is moving further away from me. But the universe is not expanding that way, that the galaxies are moving that way. Look at this piece of bread. This one has raisins in it. And the raisins could move, but that is not what is happening. That's not how the universe is expanding. The bread itself is getting bigger. So what is happening to the raisins? Looks like one raisin is moving away from the other raisin. But actually the whole bread is expanding. That is how the universe is expanding. Okay? So this is, hopefully that will help, that the expansion is not that the galaxies are moving away, but the entire space itself is expanding. Okay? That's a remarkable point that I hope you can see. Now, when we look at the universe, the dimensions are not in miles or kilometers or anything like that. Those are in parsec. It's called parsec. What is parsec? 1 parsec is 3.26 light year. And what is a light year? Light year is that light travels 186,000 miles per second. So think about how much it will travel in 1 year. And that distance is called 1 light year, and 1 parsec is even 3.26 times larger than that. Okay, equal to that. So what is 1 light year is 5,880 billion miles, and that is what light will travel in 1 year. And even that is not a big enough scale. So we use parsec, which is even larger than light year scale. Okay. Okay. So now, how do we know that the things are moving away? The optical spectra is one of the most fundamental entity of science. Electromagnetic wave, the light that is from the light coming out, that you and I can see each other, electromagnetic wave, it has electric field component going up and down, magnetic field going left and right, and the wave is moving forward. That's electromagnetic wave. And that's one of the most fundamental things. You talk about X-ray, microwave, visible light, radio wave, gamma ray, X-ray, all of those are electromagnetic waves. So what is the difference? Only difference is their wavelength, like how big is the wave. So the shorter is the wave, the stronger it is, and the longer is the wave, the weaker it is. But they are all electromagnetic wave. And this is what we are looking at, that the calcium line is coming from distant galaxies, Virgo cluster galaxies, okay? And that one is 17 megaparsec distance. This one is 215 megaparsec distance. This one is 310, 550, and 860 So these are at different distances farther and farther away. Okay. So what's happening? If we look at the calcium spectrum that is coming from this cluster of stars and galaxies, we see, okay, this one is this position here. If we look at a further one, we see that the red shift. Now, let me quickly mention, the red shift is, if you look at a fire truck is coming towards you, you see it goes high pitch. And as it passes you, the fire truck or the ambulance, then the pitch goes down. So as it is approaching you, it is called blue shift because the frequency is getting higher and wavelength is getting shorter. And as it moves away, the wavelength gets longer, frequency goes down, it is called red shift. So the red shift is one of the most useful technique to study what is happening in the universe here. And so we see that the farther distance, it has shifted to the right. This one further, and it has even shifted to the right. So shifted means it is going away at a faster rate. Okay, so that's a very fundamental scientific tools that is used in many of the scientific experiments. And so as you go further and further away, the red shift is larger and larger. It's saying that its velocity is larger and larger. Okay, it's moving away from us at a faster rate. And so, thank you. So with that, what you can do is, so let us plot this scientific data collection and plot to see what we have. So we plot velocity versus distance, and we fit a best fit curve, and that is what Hubble did. You know, Hubble telescope that you have in the sky. So the Hubble did, and he showed that, and slope h is a Hubble constant, b is the velocity, and d is the distance, and that equation shows that the age of the universe is 14 billion years. Okay. It's a very simple but a very profound result of scientific research here. So now how do we know that it is accelerating? Because it is expanding at a fixed velocity or it is going faster and faster. Accelerating means increase in velocity is acceleration. Okay, that's what is happening. And so there is one type of supernova 1 which comes from dwarf stars. Studying those and their brightness and their red shift, like, you know, what is the shift that we just went through, red shift, that how fast it is moving. By plot, it said there are two graphs. One is accelerating flat universe, one is decelerating. Decelerating means it is, the velocity is going down. That is decelerating. And the data that is found, it fits the accelerating flat universe data. Okay, so the data fits the graph where universe is accelerating. And this is one of the results. This is one of the very graph and results that resulted in Nobel Prize about 3 years ago to physicists. because it confirmed that not only that the universe is expanding, but it is expanding at an accelerated rate, faster and faster. Okay, and so now another aspect is cosmic background radiation. That how so. Here are two other scientists who did, Dr. Wilson and Penzias. They detected through radio signal the background radiation all around us throughout, in all different directions. And they found that there is a background radiation where the peak is at such a location that refers to temperature 2.73, because everything radiates, like your body radiates, this table radiates, this wall, not only this light radiates, everything radiates as long as you have any finite temperature except absolute 0K. Okay? And that distribution of black body radiation is sort of like this, and the peak of that radiation tells you what is the temperature of your body or any object. Okay? So that is a very well established physics. And so this peak of this background graph shows that the temperature from 10 to the power 37 K within 14 billion years has dropped to 2.73 K. Okay? And that is how it looks like. That radiation mapping of the entire universe that we can see looks like this. And it is quite uniform in all directions. There are little fluctuations, but otherwise it's remarkably uniform. So, model universe. How is this universe? How is it? Let me give you an example. If we have an orange, and we put an ant, little ant bug on it, and we say, okay, you go around it. So, as we look at ourselves, if we look outside, the earth looks flat, isn't it? And then the horizon. And then as we walk, it always looks flat. And we can see the horizon. This ant is going to see that orange very similarly like that. Now, if we put something in the feet of the ant so that everywhere it will go, its ant's footstep will be on the orange. Then the ant will keep going throughout its life, and then it is never going to find anything except it is going to go all over the orange, and finally he will say, oh, I have been to this place because I see my footstep. Then that way he can cover the entire orange with the footsteps of the ant. But will the ant find the boundary? Because we usually ask, well, if the universe is finite, where is the wall? What is after that? Let us ask the ant, well, you have gone through the entire universe. Have you found the wall? He said, no, because it looks like it's always the same. Cannot see the wall. But the ant has gone all over the orange. Has he found the center? No, because the center is not on the surface of the orange. It is inside at the center of the orange. So the ant could neither find the center of the universe, of its universe, or nor it could find the boundary of its universe. We are in a similar way. And so we want to see whether this universe is closed, or it is open, or it is flat. And because it is expanding, and now that one is now scientists took a different path, saying that one of the parameters that we want to see is that the critical density. If the critical density of mass in the universe has certain value, then it will be flat. If it is more than the critical density, then it will be closed. That means it is expanding. Someday it is going to come back and collapse again. Or it could be lower than the critical density, then it's going to continue to expand it at even a faster rate. Okay? So finally, after many of the research, the conclusion here now is that the universe is flat. And it is going to continue to expand indefinitely, and the critical density, which is 9 times 10 to the power minus 27 kilogram per meter cube. 9 times 10 to the power minus 27 kilogram per meter cube is the critical density of the universe, and that is what it turns out to be the case. And So in that case, we can see that is the flat universe, but what it is giving, so this is the closed, that means if the density is higher, then the universe will collapse again and will become back to the point again. Or if it is open, then it is continue to expand. Now if we look at this flat universe graph, we see that the life is 9.5 billion years, but we know that the 14 billion years is from the Hubble equation and other research. So what happened? I mean, why things are not matching? Because flat universe is saying universe is 9.5 billion years, and other data is showing is 14 billion years. Okay, that one is explained here a little bit, that this is the time of 0. And this is 10 to the power 37 temperature. After 10 to the power 43 second, the scale is second. What happened? The temperature dropped to 10 to the power 32. And that is when there are 4 fundamental forces in nature. Of all the forces that we see, only 4 are fundamental. One is the gravitational force. Like, if my glass, if I drop it, if I just let go, it drops. Why? Why does it come down? Why doesn't it go sideways? Why doesn't it go upward? Why? Because that's what Newton did, right? He was studying under an apple tree, and then apple fell on his head. He said that why it had to come down on my head, why it didn't go sideways or upward. So that is how the gravitational force was discovered by Sir Isaac Newton, that it attracts. But do we see anything? Like, if I put a hand, it still comes down. I mean, how is this earth is pulling it down? It is called gravitational force, and there is a field. If you take two magnets, two North Pole magnets, they push each other out, and North and South Pole, if you bring them, they stick together, and you cannot pull them apart. But we don't see anything. How are they doing it? But if you put two magnets, and if you put some iron particles, those particles will line up according to the field. So there is a magnetic field. That's the scientific method, that you have to either see or directly or indirectly its effect. So here are two magnets, you spray some iron particles, you'll see that they would line up. I should have had a picture of that they are randomly distributed. You bring two magnets, they will all line up like a soldier, line up like that according to the field lines. So gravitation is like that. And so there are graviton that I will talk later on, that this gravitational field, this is one. So at this temperature, the gravitational force separated. Initially, all 4 were together. Then later on, gravitational force separated. Then when it cooled down more, then grand unification theory, and this is when inflation took place. The tremendous amount of energy was released during this phase of inflation, when the temperature became 10 to the 27, and then that is when electroweak force separated from strong force, and later on at 10 to the power 15 temperature, electromagnetic force and electroweak force, they become separated. So that is what happened during this major temperature change, and the division and splitting of the 4 fundamental forces of nature that we are aware of at this time. Okay. So now what is dark matter and dark energy? So the combined mass of all visible matter or emitting any kind of radiation in the universe add up to much less than the critical density. The matter that we see, you and I see each other, we see these buildings and earth, the river, mountain and all of that, and the sky and all the materials, it does not add up to the critical density that we need for the universe to be flat. That is one. Another is that the galaxies rotate much faster than needed in apparent matter. Like, the earth is going around the sun at a certain velocity. If the mass, it depends on what is the mass of the earth, what is the mass of the sun, what is the velocity of the earth. It depends on that. So we don't get and collapse into the sun, because gravitation could pull it and crash us into the sun. Why it is not happening? That is because there is this rotational centripetal force as well as this tangential velocity. There is a balance. And so mass is a factor here. The galaxies are rotating, and the way they are rotating, the mass that we see, it is not matching. The mass is much higher then what we can see? Where are those? We cannot see them, we cannot get any radiation from them, we cannot get any measurement from them. All we see is their effect, that it is so heavy that the rotation speed is telling that it is much heavier. Where are this mass? Where are those materials? And so that is another puzzle. And then gravitational lensing shows that some clusters contain 10 times as much mass as directly visible. Einstein predicted that the mass of an object will have an effect on the radiation. It could attract and deflect. And so the stars from behind the sun, as it was coming at one time, near particularly it was during the time of the solar eclipse, that the light was found bending. And that was the instant when Einstein became world famous, because his prediction became true, that the light actually is bent by mass. Okay? And so now from this picture, the lensing effect, that when the light comes from behind some other stars, they bend and form some type of a lensing effect. And that shows that the amount of mass that you need to bend the light is not enough with the matter that we see. That this amount of material cannot deflect light like this. You need a lot more. Where are those materials? So that is where the concept of dark matter comes, that we don't really know what is the properties. It is not electron, proton, neutron material, nucleus and electron moving around. It is some other type of thing. We do not really know. So sometimes when we do not know something, either we call it X or we call it dark. So like in X-ray, the person who discovered X-ray, he did not know what to call it, so that's why he called it X-ray. But his name is Röntgen, right? And so here, since we don't know what this matter is, which is more than 90-95%, only 5% is visible, less than 5% is the material that we can see. Other is dark matter and dark energy. Those are more than 95%. But we see their effect, but we cannot really see them, so we don't know what those really are. So now, so we can see that there are materials, and we call it dark matter. And now universe is expanding instead of collapsing. So now where from this dark energy concept is coming? Because my pair of glass, if I drop, it comes down. What if it goes away from the table? That's what is happening. Why some other galaxies are moving away from us? We are supposed to be pulling each other by attraction, gravitational attraction. Gravitation has one of the properties that it always attracts. See, if you have an electron and electron, they will repel. Electron and proton will attract. If you take magnet, North Pole, they will repel. If you take North Pole, South Pole, they will attract. So magnetic field will attract and repel. Electric field will attract and repel. But gravitational force will always attract. But then what is this puzzle? Why these galaxies are moving away from us? They are supposed to be coming together and collapse. That is where the dark energy concept comes in. That the dark energy, which causes negative pressure, is causing this galaxy to move away. Okay? So that's how the dark matter concept is coming in, dark energy matter is coming in. Okay? Now, how the stars are formed? The stars are formed, as I said, that in scientific approach you need evidence, you need proof, you need data. And so here it is, looking at the sky, the gas in interstellar media, like in the stars and galaxies, there are various other dust and cloud and gases, hydrogen, helium, gas, those gases. And so those are wandering around, and those come from supernova explosion. When a supernova explosion of a star happens, then they move around, wander around in the space, and at some point they get agitated by some type of a shock. Because a lot of things happen in the space, some type of a shock, then they get agitated, and as they start moving, then they feel the gravitational force more and more. As they come closer and closer, gravitational force gets stronger and stronger, and as they come close, and then what happens? At the center, the pressure and temperature become so high that it wants to collapse. So what happens? Hydrogen gas is in there, so the temperature becomes very high, pressure becomes very high. That is when nuclear fusion starts to happen. Hydrogen atom starts to become helium. And when hydrogen becomes helium, then there is a loss of mass, and that gets converted into energy. And so this is what happens, converted into energy with this formula of E equals mc squared. And so that energy repels from the center, that you cannot collapse me. So the gravitational force tries to collapse and destroy the star, and the nuclear fusion energy through E equals mc squared is trying to counter it, that you cannot crush me. I'm going to use hydrogen will be converted into helium, and then it is going to release energy and it is going to balance it. And that is exactly what is happening with our star. In our star, our own solar system, at the center of the star, our star is struggling to survive because the gravitation is trying to collapse it, and hydrogen is becoming helium at the center of the sun, giving this nuclear energy, nuclear fusion generated energy to balance it. So what is going to happen? After the hydrogen is used up, then what is going to happen? Gravitation is going to collapse again. Then helium is going to say, oh, then the pressure and temperature will be even higher. Then helium is going to become the next heavier. It will become through some number of stages through carbon. And then carbon through oxygen. Oxygen through up to iron. And it is going to go up to iron for the star to survive. And after that, if you look at this diagram, the binding energy of elements, if you look at the periodic table, all the elements that we have in this world are about 120 or so. And out of those, iron is sitting on top of this binding energy curve. Or in other words, this is hydrogen, helium, lithium, you go up there up to iron, and then on the other side is uranium and other heavy elements. In order to give out energy through nuclear fusion process, as you add hydrogen become helium, if you go from this side to that way, then you are losing mass and you are gaining the energy, and that is going to balance the star. But after the iron, you cannot do that anymore. You cannot do that anymore because you have to actually break the heavy atom in order to lose the mass and gain the energy. So up to that point, what happens? Look at this diagram here, that at a star, at the center of the star, initially hydrogen was helium. Then when it ran out of helium, then helium became, then the next level became hydrogen to helium, center became helium to carbon. And then when the carbon got all used up, all helium got used up carbon, now carbon then it wants to collapse again, then the carbon starts to become oxygen through nuclear fusion, then oxygen, finally it becomes up to iron. Up to iron it can go to survive, the star struggling to survive. Okay, and after that what happens? It cannot support itself anymore. So then gravity finally take over, that I got you now. So then gravity is going to come and collapse it, and that is when the supernova takes place, because then it tries to collapse. And as you see, if you go to the ocean side, that big tide is coming on the ocean, but then what happens at the beach? It goes back. It comes shouting like this, and then it goes back. So as you can see that what is happening, so all these rings of so iron, oxygen, carbon, helium, hydrogen, those rings, and that's how they're surviving. And so at that stage, as it tries to collapse, then it bounces back. It bounces back in the form of supernova explosion. And that is what, this is the supernova explosion. That is what happens, is when it reaches the iron level. After that, star cannot go anymore to defend itself through nuclear fusion process. And so that is when the gravitation takes over and tries to collapse it, and then it rebounds in the form of supernova explosion with tremendous amount of energy, temperature, and force. And that is when the heavier elements, heavier than iron atoms are made. So in this world, an atom of iron from hydrogen, we have no way to make it. Scientifically, there is no way you can go from hydrogen helium atom to an atom of iron. The type of temperature and pressure that you need to go through, all of that, we have no scientific way of doing it. Only thing that can happen, only place, is at the center of the star with extremely high temperature and pressure. There is no other mechanism here on this earth that we scientifically know of. Okay? And so that is how the supernova explosion takes place. And here is an example of that. See, here is a supernova explosion, and that was observed in 1987, which is a very, very, very well-known supernova 1987A. Okay? And here is a picture of that. So, from the star as it collapsed, it bounces, and then supernova exploded. Okay, now let us come back to our sun, our solar system. Our sun is an average star. It is not a big star, it is not a small star, it is an average star. Okay, and it consists of gas, it's hydrogen gas. Okay, and it is 1 million times bigger than this planet Earth, our home. And central temperature of the Earth, of the sun, is 15 million degrees Kelvin, and that is where hydrogen is becoming helium. This is the type of temperature you need, millions of Kelvin degrees, in order to cause nuclear fusion. Its surface temperature is, of course, very cold, which is 5800 Kelvin. And the sun needs 10 to the power 38 reactions, or transforming 5 million tons of mass into energy every second to resist its own gravity. That means, in order to survive, the gravity is trying to collapse it. In order to survive and resist the gravitational force, it is converting 5 million tons of mass into energy every second. So you can see the lifetime of the sun itself. And so how was this formed? How was this formed? It was formed, the solar nebula hypothesis, which is modern theory of planet formation. This is the modern theory of planet formation, that planets form at the same time that the clouds are stars, when the stars and planets were formed at about the same time. And so what happened, that this planetary nebula, the nebula, those gas and cloud that the star was about to through some collision and through some disturbance, it got agitated and started to form the star. And so initially it is spherical in shape. It becomes spherical in shape. Then as it becomes turns, because in order to conserve the angular momentum, as it gets closer, it has to go faster. Because if you have seen ice skating, if the ice skater wants to slow down, it will extend the arm, it will go slow. But if you want to turn faster, you are going to squeeze. So this is conservation of angular momentum. It's a very, very common physics principle, that if you condense, then your rotation speed, angular speed, is going to go faster in order to keep the angular momentum conserved. And that is what happens. So in the formation of the star and the planet, so this is what happens. So from the spherical shape, it becomes plate, and from there some of the material becomes into some of these thin areas, and the center becomes more, because everything likes to go towards the center. So the center becomes the star, and the surrounding area, some of the it becomes the planets. So that is the latest modern theory, that is how the solar system was formed. And the sun, how old are we? We are about 5 billion years old. We are about 5 billion years old. And so here is the solar system, modern theory of formation, that large impact happens. Now how the moon was formed then? From this gas cloud, the sun and the solar system was formed, and the planet. What about the moon? And the moon does not seem to be same composition as our Earth. So what happened? The latest modern theory of the formation of the moon is that large impact hypothesis, that when the Earth was cooling down, because everything was gas initially, like Uranus, Neptune, those planets are still gas. Jupiter, Saturn, those are gas, but they have not cooled down enough yet. But our sun has become solid. Thank God that we have the crust. Now we can stand and walk. If you land on Uranus or Saturn, you are going to dive into the gas. Okay, so we don't have very much other place to go. Okay, so this is the place, very comfortable. Anyway, so how the moon was formed. When the earth was cooling down, then the latest theory is that there was a large impact hypothesis that this is our earth, and then something came and hit the planet earth. You see that? And then it removed a part of the planet earth from its side, and it hit at an angle. So as it did at an angle, it as it left, then it got pulled back by the gravitational attraction, so it ended up going around the earth itself. So moon is going around the earth, and that is how the moon was formed, from the earth itself by an impact by another foreign object. Okay, so that's how the moon was formed, that's how the solar system was formed, that's how the moon was formed. Now let us look at our planet earth. What is happening? The earth, even though it got solidified, inside is still liquid. You know, there are liquid portion inside the interior of the earth. That's how the volcano comes, because there are liquid, it's hot. So the crust itself, these are like plates. It's called plate tectonics. The plates are still moving. This is Pacific Ocean. This Pacific Ocean belt is moving and going down under the South America in the Chile, Peru area. And that is why as the ocean belt is going down and under the Peru, so they are pushed up. So there is a high mountain in the Chile, Peru area, high mountain, because the ocean is going down under like that. And so that is what is happening. And of course in California, as you know, that there is a plate that we get earthquake. In that situation, when it goes down, it has tremendous amount of energy involved, and that is what causes the earthquake. And also in California, the earthquake, that is plate is going sliding. It is sliding. It is not going under. It is sliding. On the left side, Pacific Ocean. On the right side is California. They are sliding. And so 200 million years ago, what happened? This is Pangea. You can see that all the continents were lumped together. And after 200 million years now, we have all these separate continents, and they are still moving. They are still moving, and so the earth is still very dynamic. And you can see the interior of the earth itself. This is the earth's crust. Then you have this mantle. This is liquid core. Inside is still liquid, and this is the heavy element core here. Okay, that's how our earth is. Now in the sun, what is happening? Little bit more, that this is how hydrogen is combining to create deuterium. 2 proton is combining, and 1 proton is becoming neutron. How can a proton become neutron? How can a proton become neutron? Because proton is positively charged and neutron is neutral. So how can happen? If it gives out positive charge, and that is called positron. Positron is very much like electron, which is positive charge, electron is negatively charged, but other properties are very similar. But when that happens, a neutrino particle also has to come out. So there are huge amount of neutrinos are coming out of the sun. Every second, huge number of neutrinos are coming out, and they are going right through all of us. Okay, because it has very high, because it's a very neutral, and it is a negligible mass, so it can go right through many things. It can go right through many things. So 2 proton combine to make deuterium with a positron and neutrino, and then another hydrogen atom will combine, and then it will give helium-3, and then those 2 helium-3 then will combine to become helium-4. Helium-4 is like 2 proton and 2 neutron. So it is not just you put 4 hydrogen and gets helium. No, it goes through this process, and due to that you get radiation. You get radiation here. Okay, here is the gamma symbol is radiation, and this is neutrino, and this is positron. Okay, all of these things are happening here. Okay, and so now what is going to happen? Once the sun has used up its hydrogen, it is going to go to helium conversion, helium to carbon, carbon to oxygen. At about that stage, the sun is not big enough to go up to carbon. And that is when it is going to expand as a red giant, and then it will expand and will become big enough to, because say here is sun and the earth is going around, the sun will expand to the orbital path of the earth. And that is when, see, sun will expand to the earth's orbit. Earth will then be burned to ashes by the sun before the death of the sun itself. So that about the time the sun itself will die, but before that it will expand to grab the earth. And that is how that will be the end of the earth itself. The sun may form a planetary nebula, but not uncertain. Sun, carbon, oxygen core will become a white dwarf. Our sun will become dwarf, inactive. It will cool down with time, but it will die as a star. It will have no other energy to give light. And so that will happen in about 5 billion years. So because it is about halfway life. Okay, it's about midlife of our sun. Now let us look at now we have looked at the moon, we have looked at the earth, we have looked at the sun. Now let us look at the galaxy where we belong. Our home is Milky Way galaxy. How does that look? This is how it looks. Structure of Milky Way. This is how our Milky Way looks. It's like spiral. It's like a spiral galaxy. Galaxies can be a spiral galaxy, or it can be like elliptical galaxy, or it can be sort of irregular type of galaxy. Ours, Milky Way, is a spiral galaxy. And look at this. Where is the sun? Where are we? Do you see this little wing over here? Over there, see a little dot here? And that is where our sun is. And that is where all its planets are. That is where the moon is. At this tiny little wing, that's where we are. And if you look at from the side, this is our Milky Way galaxy, and this is the central bulge. That is where most of the stars are. And this thin area, somewhere in the middle out there, is our sun. And around that sun, we have these 8-9 planets. And of that we have a moon. When I first saw this picture, I had my tears. It looked so insignificant. In this galaxy, we are not even at the center of the galaxy. We are of the far on a little leaf wing, a tiny little star, and on those are the planets. And on this little planet, we are 7 billion people, and I am one of those. It made me cry. We have nothing to be proud of. We need to remain very modest. We need to remain very humble. And so, okay, now the sun itself is going around the center of the galaxy, Milky Way galaxy. How fast it is going? How far are we all going with our sun? 220 kilometers per second. So how long it will take for us to go around the entire Milky Way galaxy? 240 million years. So one time the sun will go around the Milky Way galaxy, it will take 240 million years. That's how at the speed with which we are going. Okay, and so our Earth. So Earth is going around the sun. Earth is also rotating on its axis to give day and night. Going around the sun is giving the year. And then it is also precessing like a top. And so right now the Polaris is our North Star. It will precess. Its precision takes 26. The precision takes 26,000 years. 26,000 years. The Earth itself, not only it goes around the sun, it rotates, it spins to give us day and night, and then it precesses. It rotates like this. That takes 26,000 years, and then we are going with the sun around the Milky Way. That will take us 240 million years. So we have all kinds of movement going on. Okay, even though we don't feel that. Okay, many types of movement. Okay, so our sun is going to be, now this is all the stars, at a cluster or galaxy, and this is what is very, very, very commonly used by scientists that, to study that. It is called HR diagram, where you can plot the main sequence stars, and then the red giant, the super giant, and the dwarf stars. And here is our sun, right there. It is not, there are other bigger stars, there are other brighter stars, but how come the sun is the brightest that we see? Because it is very close to us. But there are other stars, they are much bigger, much brighter, and much more activities going on. But how come they look small? Because they are so far, far away. Okay, so our sun is here, and then what it is going to happen? It is going to become, once it gets convert all the helium into carbon oxygen, it is going to become a red giant, and that is when it is going to engulf our planet Earth. Okay. Here is our Earth, here is our sun, and here is the Earth going around the sun, and here is this our zodiac constellation, which we are very familiar with, right? Okay, so we have this Cancer, Leo, Virgo, and all those 12 constellations that we go through throughout the year, right? And here is the picture of that, and here is the moon. Here is our planet Earth. That one is, the Earth is going around the sun, and what we see in the sky, okay, in the celestial sphere. Celestial sphere is the sky that we see with all the stars, and the sun we see is tracing along those zodiac constellations. Okay, and here is the Earth and the moon. And when the moon is here, if the sun is on this side, moon is here, then from this planet Earth we see crescent moon. Then the moon grows, and when it comes here, it becomes full moon. Then when it comes back to the moon disappears, and it becomes full moon again, and it keeps going around. And that is how the crescent moon, and then it grows full moon, and then it becomes smaller again, and it disappears, and then it becomes full moon again, crescent moon again. So that's the cycle. Okay. Now, another important thing I want to mention here is that the moon takes only 27 days to go around the sun. Around the earth. Moon takes only 27 days to go around the earth. So how come we take 29, 30 days? That is because the earth is moving around the sun. So moon has to keep up with it. So it needs another 2 days to keep up with the earth, because it is going around the sun. Okay, so those two numbers are called the 27.32, it is called sidereal period, and then the other 29.53, it is called synodic period. Okay, so just for you to know that moon takes only 27 days to go around the earth, but earth itself moved. So to keep up with that, to be relative to the same position as the sun, it needs 2 additional days to come back to the same position. Okay, so now what is neutron star? Neutron star is that if the sun is a supernova explosion of m greater than 8 m sun, some stars that are about 8 times bigger than our sun, if it is that big, after supernova explosion, it blows out the outer layers. It blows out the outer layers. Okay? And so, then what happens? The central core will collapse. Now, whatever is left, it is going to collapse now. It is going to collapse again. And it is going to collapse to such a density that electrons and protons will combine to form neutrons. I mean, think about this. Now that the supernova explosion, those are gone. Now the star is not safe still. Gravitation is going to collapse it again. And as it will collapse, the electron and proton will get smashed. And what happens? Proton and electron, if you smash them positive and negative charge, it becomes neutral, it becomes neutron. So the entire star itself, see, combined to form stable neutron throughout the object. The entire object becomes neutron with such a tremendous amount of pressure. Okay? And so that is called neutron star. And so its density is 10 to the power 14 gram per centimeter cube. A piece of neutron star matter size of a sugar cube, you take T in a sugar cube, that its mass will be 100 million tons. That is how dense it is, because atoms are very vacuum. Because nucleus is at the center, electrons are outside. The atom is a vacuum, like, empty space. Neutron at the center, heavy, and the most of it is empty, and then electrons are moving outside. But this collapse, condense electron, brings it to the proton and makes it and becomes neutron. So density becomes so high that one sugar cube is 100 million tons. Okay, that is how dense it is, and it becomes like a lighthouse. It gives light. These neutron stars. Okay, and so that is how their characteristics has been measured. There is a very strong magnetic field also in the neutron stars. And okay, now what is black hole? Neutron stars cannot exist with masses 3 times the sum of the mass. Look at this. After converting up to iron, then it started to collapse because it has no other to defend itself, no other way to defend itself. Then it collapsed, and then supernova explosion took place, and then it collapsed again and formed it into neutron star. That is not the end of it. If that star is still big enough to be 3 times the mass of the sun, then this collapse is going to continue. So we know of no mechanism to halt the collapse of a compact object with greater than three times the mass of the sun. There is no way, even in the form of the neutron star, it cannot. If it is big enough, that gravitation will be high enough to even collapse that neutron star. So where do we go from there? There is no way to stop. Nothing else is left to stop. It is going to collapse into a single point called singularity, and that is a black hole. That is a black hole. It becomes a singularity. We have no idea what is it at the center. Okay, and so what happens? Velocity. Now the mass is so high, density is so high in the black hole that if we can throw an object from the surface of the earth, if you can throw it at 11.6 kilometer per second, if I can throw my glass at 11.3 kilometer per second, it will leave the planet Earth. If it is 8.2 kilometer per second, it will orbit like a satellite. And if it is 7 kilometer or anything less, it is going to come back and drop like this. It's going to come back and drop like this. Okay. So what about the black hole? We have to be able to go event horizon escape velocity. You have to be able to, as the mass gets larger and larger, you have to have a higher and higher velocity to escape. But there is nothing that can go faster than the speed of light. So what will be the mass that will require the escape velocity to be the speed of light, which is 186,000 miles per second? Even that, the horizon that determines that speed of light escape velocity is called event horizon, and its escape velocity is c. We have no way of finding out what is happening inside that Schwarzschild radius. So this is an event horizon, and this is the Schwarzschild radius, and anything that goes inside it cannot escape even with the speed of light. So once it is gone inside, it is gone forever. We will have no way to know what happened inside there. Okay, so that is black hole. And so what about our Milky Way? There is a black hole in the center of our Milky Way. So measuring the mass of black hole in the center of the Milky Way, what is its mass? 3.7 million solar masses. 3.7 million sun, if you put together, that is the mass of a black hole. Okay. And okay, so there is there is the black hole at the center of our Milky Way. So now what is going to happen? Say if any of you want to be adventurous and we want to go and see the black hole, so you start to land on the black hole. Okay, so what happens? The gravitational acceleration due to gravity, the g, small g, acceleration due to gravity gradient, because the mass is so dense, so high, that as you land on it, the acceleration due to gravity is so high, even within the distance of your length, that your leg is going to get elongated like this, while your head is still, different. So do you see the effect? Do you see the effect that if you want to land, your leg is going to get pulled out so much stronger compared to the upper part of your body, that is how we are going to shape before you even can get to the black hole. Okay? And so that is the effect of black hole. Now graviton. Graviton, as I said, that the gravitational force that the earth attracts us, and that one is the electromagnetic wave I talked about, that electric field, magnetic field, and then electromagnetic wave moves forward. The quanta of electromagnetic wave is called photon. Quanta of electromagnetic wave is called photon. So the quanta of gravitational force is called graviton. It's called graviton. Okay, and so there has been a lot of attempts to detect the graviton, that how is this earth is pulling us, how this gravitational attraction is taking place. And so that is what happened, that I talked about this cosmic radiation background. Light can be polarized because the electric field component can be in all different directions. But polarization means that electric field will be only in this direction. Anything that is this way or that way can be discarded. You can polarize. A polarizer lens can do that. And so the polarization effect on that background radiation has been connected with the interaction with the graviton. Okay, so recently they have detected certain polarization effect on the cosmic background radiation itself, and that is now being referred to as the effect of the existence of the graviton. Okay, and that actually became a very big news worldwide only a few months ago. And so that is that also confirms the Big Bang and also the inflation stage. Okay, and now Higgs boson. Now Higgs boson is that we always felt that space is empty. Space is empty. But Peter Higgs, he's a professor, and he predicted another elementary particle. And he called it Higgs particle or God's particle or Higgs boson. And so what is it? It is just an elementary particle. And how that experiment was done, here is the result of that experiment that was done in Europe. And the effect was that two protons were brought into collision with extremely high energy. And when the two protons collided, and they saw the effect, and that is where they traced back and analyzed and said that this is the Higgs boson detection. Okay, and so Higgs field is invisible energy field that exists everywhere in the universe. So Higgs field, now we have another field now here, gravitational field, graviton, electromagnetic field, photon. Now we have Higgs field, Higgs particle or God particle or Higgs boson. Okay, so that is how. And so another effect of this Higgs field is that the mass of an object, how an object, like, this one is like 2 kg or, half a kg weight, mass. How is it coming? So in this Higgs field, the analysis is that the object from this Higgs field, and as an object moves into space through this Higgs field, it is going to interact with Higgs particle and get mass from this field. And that is how it has been explained, that scientists assume that vacuums usually actually had energy, and that way, if a particle that we think has massless were to enter into the energy from the vacuum would be transferred into that particle, giving it the mass. That as the particle moves through this Higgs field, then the energy will be transformed to that particle from the field to give its mass. So that's a very different way. Like Newton said, what is mass? Anything that occupies space is mass. And Einstein said that mass is actually space bending. Now Higgs is saying that the mass is attained by an object as it travels through the Higgs field. So Higgs field energy is transferred into object, giving it its mass. So this is a remarkably very different way of looking at the universe where we live and what we are. Okay? And so now neutrino, and some time ago you saw that neutrino, they found that the neutrino speed is faster than the speed of light. Well, the problem is that it turned out that what is so neutron, when a neutron becomes proton plus electron, and there is a neutrino. Okay? And so that's how we get neutrino. Now, what if the neutrino had a speed that is higher than the speed of light? There is a time dilation. This time, we call it 3 hours, 4 hours, those are all very relative things. If you have a twin, you have heard of twin paradox. If you have twin, one twin is going to go into space with nearly the speed of light, and he will come back and he will see that his twin brother has grown much older. So not only that the time, the whole clock, the whole biological clock, its speed, its timing speed changes. It is very difficult to see, very difficult to conceive that how is that possible, but that is what this world and universe is where we live. And so if neutrino had a speed which had equal to the speed of light, then b square and c square will become equal, 1 minus 1 will become 0, and so t0 times 0 divided by 0, what is going to happen? T0 divided by 0 is infinity. It will explode, it will blow up. So whole physical meaning will collapse. So everybody became very worried that why this neutrino has the speed equal to the speed of light or greater. If it is greater, then it will become even imaginary. So, but it turned out that they had some experimental setup error. So the speed of the neutrino is still not exceeding the speed of light. Light speed is still the highest. Okay? And now basis of life. Now this is the last thing that I'm going to talk about. Basis of life. All life forms on Earth is carbon chemistry. The carbon that we are formed with the center of the star, our body is filled with carbon atoms. Carbon, oxygen, hydrogen, silicon, those are the ones that make carbon, hydrogen, oxygen, silicon, those make most of the part of our, not only ours, but just in general the life. And so carbon-based DNA and RNA molecules are the basic carriers of genetic information in our life. Okay, and those are the amino acids, A, C, G, T, those are the names, and this is how our DNA is A, C, G, T, those are the amino acids. Okay, so people wanted to understand that where from we came and how we came and all of that, and so here is a Professor Miller. What he did is he took carbon, hydrogen, nitrogen, oxygen, and all of that, and he used this experimental setup electrode and sparking, put a voltage shock, and he was able to, the experiment produced some fundamental building blocks of life, amino acids, fatty acids, and urea. So he was able to form amino acid in the lab, okay? Because that is the fundamental basis of life, to see how it came, because people are trying to understand where from this life came. There was another group who was trying to see that did we come from another another place, and the theory is that some meteorites do show traces of amino acids. Meteorites, which have bombarded the planet Earth many times, and it still does. So some of those meteorites showed the trace of amino acids. Okay, so those were, but that is not a very Currently, it's not a very strong direction of research right now, but they did see some amino acid. Okay, then fossil under the ocean. Under the ocean, 3.5 billion years ago. Some fossils are 3.5 billion years ago, but those are under the ocean. And then life on Earth. See, 500 million years ago, though these are still underwater. And it is only, there is no trace of life on land until 400 million years ago. So the life under the water in the ocean is 3.5 billion years. Some fossils are there, like microorganisms are that old. And then, but on the land, there is no trace of life beyond 400 million years. And so here is a geologic time. Time is that if we go from the beginning of the Big Bang up to this point, 14 billion years, then the human have existed only 3 million years. The dead bodies and some other leftovers and fossils and all of that. Humans trace 3 million years. Now, if we put it in a scale, that Big Bang is January 1st, February, March, April, all those things that happened, then the human life is only in the last hour of December 31st or December 31, 11 hours and 59 minutes and few seconds. That is where human life started on this planet Earth. Okay, now what about other place? Mars was the only place where we saw in other planets some water, but trace of life proof is still very weak. Okay, so what do we need for life to exist elsewhere? Are there life elsewhere? It is very curiosity of human being on planet Earth has been for a long time. So what do we need? We think that the life will be very similar to our time, the way we have. So it is going to look at some planetary systems are probably common, that other stars will have planets. Orbit around the star, they have to orbit around the sun. A single star, because many of the stars in the sky, they are binary stars, they are twin. Two stars, they rotate together. Like human being couple, stars are also couples. They're together. About half of the stars in the sky are binary, two. They stay together. Okay, they rotate around each other together. But star has to be one, because our sun is one. And then time of evolution, consider only in a less massive star, moderate temperature, because if it is too hot, then there will be no life. And life zone around the star. And so, we try to communicate. So from the Earth, an Arecibo message was sent out in 1974, which was about 40 years ago. And that was a signal of 23 by 73, which is 1679 pulses were sent out, emitted into space. Okay? And that had the information of this is how we look like as a human being. We have our sun, we have our planet Earth, and then we are made of DNA, and then we have hydrogen, carbon, nitrogen, oxygen, and phosphorus. We count binary number 1 through 10, and then all of these things, this is how we look like. This message was sent out electronically in 1974. We have not heard something back yet. Now, how can we receive it back? Can we receive the signal back? The problem is, once again, the only way that we can get the information is through the electromagnetic wave. Only through the electromagnetic wave, the light, at various different frequencies and wavelengths. And so, when we look at these wavelengths, this is in centimeter scale wavelength, and this is the signal strength. These wavelengths cannot come to the Earth because it gets absorbed by the galaxies and other in the sky. On the other side, if the wavelength is very, very short, then it gets absorbed by the Earth's atmosphere. So only in the middle, we call it water hole. We call it water hole. That is the spectra that comes from hydrogen and OH. Okay, we call it water hole, and that is the only window where the signal can come and we can try to see, try to get any communication going through them. Okay, so this is the last slide. Life in cosmos. Number of stars per galaxy. So let us take a galaxy to see what is the probability that there will be a planet where there will be life. Okay, so here are the probability factors here. Number of stars per galaxy, this much, which will be like 200 billion. Our Milky Way galaxy has 200 billion stars. 200 billion stars only in our Milky Way galaxy, and there are other millions of galaxies. There are other millions of galaxies in the universe, and only in our galaxy there are 200 billion stars. Okay, and so just this one is taking just one of the galaxies like that, which has 200 billion stars. And so fraction of stars with planets. So how many of that star will have planets? Say if it is 0.1. Number of planet per star that lie in the habitable zone for longer than 4 billion years. That those planets will stay in a place where it will live for more than 4 billion years, just the way we have survived. What is the probability of that? So that is 1. Okay, 0.01, and then fraction of suitable planet on which life began. Now, what is the probability that that planet, life will be able to grow, because our Jupiter, Saturn, there is no life over here. So what is the probability of that? That one is again 0.01. Fraction of planet life where life form evolve intelligence. So only life is not enough. What is the probability that the life will become intelligent? You know, that probability is also considered here, which is 0.01 again. Fraction of stars existence during which technology society will survive. That, you know, we have intelligent, but how can we become technologically advanced so that we can communicate? Okay, so what is the probability of that? And that probability is taken 10 to the power minus 8. And then last condition, number of communicative individualization per galaxy. That one, they may be intelligent, they may be able to communicate, but are they going to communicate with us? And what is that probability? That probability is taken 2 times 10 to the minus 4. So what is the number of planet where there will be life in our galaxy? And we put all of these factors, N, F, S, you know, all of those factors. It turns out that the value comes to about 1 communicative civilization per galaxy. The probability that a galaxy will have 1 planet that will have life, where those life will make an attempt to communicate with us. So here it is that 1 communicative civilization per galaxy, but then of course there are millions of galaxies. So that is the hope, that we'll have some friend somewhere